Hey folks, today we're going to be talking about acids and bases. So this is building off of our understanding of aqueous solutions. Now, aqueous solution is just a fancy term for things that are dissolved in water. And one of the only ways in which acids and bases can work is if they're dissolved in water. So let's talk about some of the properties that acids and bases have. So acids typically have a sour taste to them. Maybe, for example, you've tasted a lime or a lemon before, and you're like, "Ugh," or maybe you've given it to a baby, and you're like, "Hey, that's funny." But the idea, ladies and gentlemen, is that most acids have a very sour taste, and that's actually how they used to determine whether things were acidic or bases by, oh, dare I say, tasting them back then. We don't do that anymore. Not recommended because, oh, yeah, they could probably kill you. Um, Acids do change the color of an acid-base indicator. So for any of you who have used universal indicator or maybe you remember litmus paper, ooh, yeah, the blue and the pink paper, yep, that would also change the color of it. Now, some acids do react with metals and release hydrogen. All right, this is why we don't want to pour, for example, acids down the drain unless we know that the pipes, ladies and gentlemen, are made of plastic. If they're made of metals, they could actually dissolve away the pipe, and then you get what's called a broken pipe. And if it's a sewer pipe, ooh, all sorts of stinky. And then when acids react with bases, they will produce water and salts. And then finally, acids are fantastic conductors, meaning that they are great. Oh, a term to be used from the last presentation, electrolytes, ladies and gentlemen. Okay. Now let's look at bases. Okay. Bases, on the other hand, have a bitter taste. And that's how I remember that bases are bitter, is because they both start with the letter B. And you're like, what does bitter taste like? If you've ever had really strong chocolate, like really like pure cacao. Oh, sorry, that's just all sorts of weird. But if you, for example, have anything that has a very high concentration of, for example, chocolate, it will have a very bitter taste. It's not sweet by any measure. Bases change the color of acid-base indicators, and they also, this is one of the unique features, is when they're dilute in a solution, they feel very slippery to the skin. So what you'll notice is like things like soaps or detergents have a slippery feel to them, and that's because they are basic in nature. Bases will react with acids to produce salts and water, and they are also fantastic, oh, dare I say again, electrolytes. Now, if you were paying attention, you'll notice that some of these cross over, meaning between acids and bases, they have the same similar properties. And yes, the big ones that you need to make sure that you know that they cross over are that they change the color of an acid-base indicator, so an indicator of some sort. They are very good electrolytes, and they will react with each other to form salt. And you're like, what the heck is a salt? Well, it's an ionic compound. That's just a fancy term for a salt is an ionic compound, not sodium chloride. I know we use that term a lot. Ooh, it's salt. Salt is a general term for an ionic compound. So let's discuss some of the theories that go along with acids and bases. Now, recognize this is what we call a theory, ladies and gentlemen. Okay, so until we have other information, this is what we know up to this point. And there are two of which that you need to know. They are starred here. We have Arrhenius and we have Bronsted-Lowry. We're not going to be going over what are called Lewis acids and bases. You can get that in AP chemistry for those of you planning on doing that. Lucky you, but you do need to know Arrhenius and Bronsted-Lowry. Okay, so let's start with Arrhenius. Now, Arrhenius was the first to come up with the idea of what an acid and what a base is by looking at what it produced. And in particular, Arrhenius made the definition that acids are hydrogen ion or hydrogen containing compounds that ionize, meaning form ions of hydrogen ions in aqueous solution. Meaning, when I put a substance that contains hydrogen in it, it will produce hydrogen ions. Pretty damn simple, okay? Bases, on the other hand, are hydroxide containing compounds that ionize, meaning form ions to yield hydroxide in aqueous solution. Okay, so it's a very good definition of an acid and a base. However, the problem is it was a very narrow definition. And let me explain what I mean by a narrow definition by looking at the other theory of acids and bases, which was Bronsted-Lowry. Now, this is not saying that Arrhenius was wrong, it was just a narrow definition. Okay, so Bronsted and Lowry wanted to come up with a better definition of an acid versus a base. And so they came up with the idea that an acid is a hydrogen ion donor, while a base is a hydrogen ion acceptor. So if you donate, you're giving. If you are an acceptor, you're taking, okay? So let's go ahead and look at this example here. This, ladies and gentlemen, is good old-fashioned ammonia. Oops, 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 back, abort, abort. There we go. We have ammonia here, all right, NH3, okay? Now, NH3, if you look at this, you're like, oh, this is so going to end up being an acid because it's got hydrogen and it's got nitrogen. So when it reacts with water, it's going to form some type of hydrogen ion compound. No, no, wrong, wrong, wrong. What actually happens is that the ammonia here will take a hydrogen from the water and form ammonium and produce hydroxide. So this, ladies and gentlemen, becomes the what we refer to as the base, and this becomes the acid. Okay. All right. Now, if you notice, the arrow is going in both directions. Okay, which means that this is in equilibrium, meaning as fast as this base is formed and reacting with acid to form the ammonium here and the hydroxide, it will reverse its course. So that means that this, ladies and gentlemen, the ammonium will react with the hydroxide to reform the reactants, okay? And if we look at this definition, this would be the acid and this would be the base. Now, we don't call them acid and base, we actually call them what are referred to as conjugate, okay? Conjugate acids and bases. So this would be a conjugate acid and this would be a conjugate base. And you're like, conjugate? What's conjugate? I've heard of conjugation of verbs in like Spanish. And for those of you who have heard of that, yes. Is it related to that? Absolutely. They're built from it. Okay. Let's look at another one. Here we have HF and H2O, and we end up with this here would be the acid, and the water here is acting as the base. Okay, so what we end up forming is we end up have the idea of fluoride, and this represents the acid component. Okay, so here we get base, here we get acid, ladies and gentlemen. So this would have a slippery feel to it. All right, and this, on the other hand, would have a sour taste, okay? Now, I do not recommend tasting it, so we need to come up with a better way to measure whether it's an acid or a base. And one of the things that we can do is we can look at the strengths of acids, all right? And there are varying strengths of acids. They are not all the same. And so what we want to first look at is strong acids, okay? Now, strong acids, there's actually only 7 strong acids, all right? And one of which is HCl. And by definition, a strong acid is one that completely ionizes in aqueous solution, meaning all of the hydrogen comes apart from the chloride ion, okay? Everyone got that? So here's what we're talking about. In this, and you know, look, see the arrow? Look. Do you notice that the arrow is going in one direction? That means that it cannot reverse itself, okay? And so what ends up happening is that we get 100% ionization, meaning all of it goes to product. For those of you who don't like words, there are pictures. Ooh, pictures. So if we look right here, this is the acid. This is representing the HCl, okay? Reacting with the water. And notice that it forms the hydronium and the conjugate of that, okay? And so we end up, this would be the Cl minus here. This would be the HCl. You notice that there is none of the other reactant remaining here, okay? And so that, by definition, is a strong acid. So therefore, let's talk about the weak ones, okay? So in weak acids, they do not completely ionize in aqueous solution. And in particular, I'm going to pick on acetic acid, which is just a fancy word for vinegar, ladies and gentlemen. Yes, and you're like, oh, I eat weak acids? Yes, you do. You often have weak acids. If, for example, you've had any type of citrus fruit, you've consumed weak acids, ladies and gentlemen, okay? And so when you eat, for example, certain types of peppers, you're consuming a weak acid. And so when it dissociates, it does not dissociate completely. And oh, look at the arrow here. It's going in both directions, suggesting that it's reversible. So what this actually means, ladies and gentlemen, that 95% of it, greater than 95% of it, is in this particular portion, and less than 5% of it is in this state, which is meaning that it's forming the acid and its conjugate. So therefore, it is considered to be a weak acid. And for those of you who don't like words, oh yeah, there are pictures, okay? Notice here, this is the original acid, right? Reacting with the water, but notice how much of the original acid we have remaining. A ridiculous amount and a very small quantity of the actual acid that is produced. Now, what does this mean? Well, it just means that it's not as strong. Can it still do damage? Absolutely. Okay, absolutely. I mean, strong acids will do more damage at a faster rate than, for example, weak acids, but weak acids over time will do just as much damage as a strong acid. Okay. So how do we measure all this? We use this thing called pH. I am sure that you have heard of pH before, okay? But probably in a very limited definition. So let's talk about pH. So pH, all right, is measured when we measure the amount of hydrogen ion that is in solution, okay? So we're looking at what is called the hydronium or hydrogen ion. So hydronium is what we've been seeing as H3O plus. Okay, so and the hydrogen ion. So this is what happens when you have water. Now, when it reacts with water. Now, did you know that when you drink pure water, which none of us do, we've already talked about this, right? Aqueous solutions, we have tons of stuff dissolved in water. But if you were to drink pure distilled water, it would also contain a very small quantity of hydronium and hydroxide in it. Yes, you're drinking an acid and a base simultaneously. And you're going, wait, hold on. If I'm drinking an acid and a base, why is it that I don't get the burning and the slippery sensation? Well, because the thing is they are in perfect proportions of each other, meaning equal proportions, which really means if we look at this, ladies and gentlemen, we have the reversible arrow, which means it's less than 5% of this, okay? Very small proportion of it, all right? And this is referred to as the self-ionization of water. This occurs very, very little in water, less than 5%. Yeah. So what this means, all right, is that we can calculate, and there's a relationship between hydroxide and hydronium, or hydrogen ion, okay? And so in pure water, the concentration, these brackets represent concentration in molarity, ladies and gentlemen. The concentration of the hydrogen ion, or the hydronium, is 1 times 10 to the negative 7th. And the concentration of the hydroxide is 1 times 10 to the negative 7th in pure water. Now, does anyone 7? Why does that number sound familiar? 10 to the negative 7. Huh, fun. Oh, wait a second. If you know anything about the pH scale, wait a second. What is pH? Wait, hold on. Neutral 7, isn't it? Huh, I wonder if this little exponent has anything to do with pH and the measuring of pH. And so this solution that you'd be consuming would be neutral. And so what is pH? pH is, by definition, the negative log of hydrogen ion concentration. You're like, oh no, not logs, anything but logs. Well, let's think about logs for a second. Logs are on the base unit of 10 typically. Okay, so what we're talking about here, ladies and gentlemen, is that we can actually determine the pH of a substance by looking at its hydrogen ion concentration. And if, for example, let's say the hydrogen ion concentration is times 10 to the negative 7th, ladies and gentlemen, the negative log of 10 to the negative 7th equals 7. Oh yeah, I just said that, 7. That is what we consider to be neutral. So what if the hydrogen ion concentration was, for example, equal to 10 to the negative 3rd? Oh, you're like, hey, that means the pH would be equal to 3. Hey, now, What does this all mean? Well, what this means, ladies and gentlemen, is that a pH of less than 7 is going to be considered acidic, a pH of 7 is exactly neutral, and a pH of greater than 7 is basic, okay? Now, you're going to say, okay, so if I have a pH of, for example, 1 versus a pH of 2, really, what is the difference? It's a 10-time multiple of each other, meaning it's 10 times the concentration between the pH of 2 versus a pH of 1. 10 times. One change in pH, one full number change, is 10 times the amount of concentration of that hydrogen ion. So that's why when we have just a small change in pH, it makes a huge difference. Let's talk about our blood. Our blood has a certain pH. It usually stays around 7.2. And we can actually have it, or 7.4. And we can actually get it down to like 7.2, but then we get into this acidosis phase, okay? Really dangerous for our body, all right? And so that's what happens when we breathe in too much carbon dioxide, is we can end up creating it to where our blood becomes slightly acidic, okay? Hence the formation of some, oh, dare I say, lactic acid stuff. Related. Interesting. Okay. Now, this is the general scale for hydrogen ions and hydroxide ions. We can see here, ladies and gentlemen, that for hydrogen ion here, we can see that the pH is 0 and 1 and 2 and so on and so forth, and they're related to each other. They are an inverse relationship to each other. So if the hydrogen ion concentration is, for example, 10 to the 0th power, that means that the hydroxide ion concentration is 1 times 10 to the negative 14th power. Okay, so they are related to each other, but when they're equal, we have a pH of 7. So everything here is acidic up here in this region, and everything here is basic in this region. And we'll get into more detail how important acids and bases are to us in our daily life.